Hello everyone. We're going to examine in this video some applications of geometric sequences. Just as a reminder, recall that we have introduced the concept of geometric sequences in a previous video. Two elements were highlighted, namely, the terms of a geometric sequence always follow a pattern that can be expressed in the form ak equals a0 r to the power k. K is a changing variable that takes on values usually 0, 1, 2, 3, and so forth. The geometric sequence is always such that its limit goes towards 0 when the ratio is between -1 and 1, and it diverges in all other situations. So an application is one called exponential growth. For instance, a certain bacteria can reproduce at a rate that doubles its population every hour. The size of the population is 3,000 when the bacteria was detected. Now, write the geometric sequence that shows the hourly evolution of the bacteria population. We're going to write the population size in thousands so that we don't drag a bunch of zeros around. The initial bacteria population, so let's call it P0, is 3. This would be the initial term of the geometric sequence. After 1 hour, P1, the population size will have doubled. So it'll be 2 times the initial population. So 2 times 3 is 6. After 2 hours, P2 is 2 times what it was after hour number 1, which is basically 4 times. So 2 squared times P0. And likewise, after 3 hours, we're doubling the population size that was viewed after 2 hours. And that's like doing 8 times, so 2 to the 3 times the initial population size, so 24. 3, 6, 12, 24 shows that the population size doubles at every consecutive hour. So k hours after having discovered the presence of the bacteria, we can predict that the population size, still written in thousands, will be P0 times 2 to the power k. Every hour adds a multiplication factor of 2, which is playing the role of the ratio. So in other words, pk, in this case, is 3 times 2 to the k, 3 being the initial term, 2 being the ratio. Exponential decay is another application of geometric sequences. So we can estimate, for instance, that on an annual basis, 1/5 of oil reserves are being used. Suppose that 250 billion barrels of oil are currently available. Let's write a geometric sequence that shows the annual evolution of available stocks in oil, counted in billion barrels. Once again, there is the initial value, or the first value of the sequence, which is 250. I'm going to call that B0. B for barrels, and 0 for at the initial time frame. After 1 year, we will have 4/5 of what initially was available in terms of oil. 4/5 because 1/5 was used. So 4/5 of B0 is 200. After 2 years, 4/5 of what was available after year 1 is still left, or if you prefer, 4/5 squared of what was initially available at time 0. And after 3 years, 4/5 of what was available after 2 years, or 4/5 cubed compared to what was initially available at date 0 to 128. So here is the evolution in time. You'll notice that we have used a constant ratio of 4/5 throughout this process. 250 was the initial value, so it played the role of a B0, and therefore we can anticipate that in n years, the amount of barrels, or the amount of million barrels available, Bn, will be 250 4/5 to the n. This time, since the ratio 4/5 is between -1 and 1, we can even anticipate that very far in the future, so as n goes to infinity, the available barrels of oil will go to zero. Now for us, the most interesting application of geometric sequences will be compounding interest. Suppose $500 are deposited into an account that bears 0.5% interest per month. Write the geometric sequence that shows the monthly evolution of this amount. Notice how the interest rate that is given is counted in months, and that the time spans that we will examine the value of the investment is also monthly. So initially $500 are available. That would be the value at time zero or at date zero of the investment. After 1 month, V1 is the value of the investment, and it will be equal to what we had initially, $500, to which is added 0.5% of the investment. You'll notice that V0 is common and can be factored out to leave V0 times 1.005, or 1 plus 0.5%. So after 1 month, the investment is now worth $502.50. After 2 months, the value of the investment depends on what the amount was available after 1 month and 0.5% added to that amount. So it's 0.5% of V1 that is added. Once again, V1 this time is common and can be factored. So V1 is multiplied by 1.005, but V1 itself was obtained from V0 times 1.005. So it's actually like so the amount after 2 months is equivalent to the initial amount to which interest was compounded twice. And that's represented by the term 1.005 squared. So 2 compounding effects over that time period. So if we've taken note of the pattern, we can assume that n months after it was originally deposited, we can predict that the investment's value will then be 500 times 1.005 to the power n. It worked when n was 1, it worked when n was 2, and this compounding effect will keep acting. In terms of compounding interest, observe that a geometric sequence can be used to compute the value of any investment using the following rule. So Vn is V0 times 1 plus I to the power n. So that will be a shortcut for us. The sequence's ratio, so playing the role of the R, is 1 plus I, where I is the periodic rate, so it could be monthly, could be daily, could be annual, as long as it corresponds to n, which is counted using the same time periods. For instance, find the value of a $12,000 investment that bears 2% quarterly interest 10 years after it was originally deposited. So the original deposit is $12,000. That will be the initial value of our geometric sequence. Since we are using quarterly interest, then we must also count time in quarters. And quarters are 3-month periods. So there are 4 3-month periods per year, and over 10 years, that would mean 40 quarters. So after 10 years, we're basically looking for V40, 40 quarters later. And according to our geometric sequence formula applied to compounding interest, V40 will be 12,000, so the V0, 1 plus I, 1 plus 2% to the power 40, $26,500.